Anybody have a question to get us started? This could be a quick session. Nobody has a question to get us started. Maybe I'll go to yesterday, to that list. It seemed like, in my, just a little while ago, I was thinking, there's something else I should have, can't find my list. When I went over the test format, it seemed like there was something else I should have mentioned on here. But I can't think of what it is now. Guess that's good. So, has anybody thought of anything?
Do you have any old tests that we could use to practice?
Um, yeah, I don't know that they're necessarily good old tests, but I do have one. The problem is I don't have any solutions for it. I don't have a, but I could open it up here and I could get it to you somehow, probably through Google Classroom. Let me just look here. I can dive into all my folders. Physics 200. We're in chapter 18. You can see I'm not very organized. So this is all new stuff. But if I go back, I was just looking at this the other day to maybe 2017 or so. I had an old quiz that I ran into. Quiz study guide quiz. Let's see. Maybe this is. I was calling it a quiz back then. That's not it. Okay, so this was, this was kind of. It was very different than how it is now. So here, I wanted them to actually know what the metric prefixes were. I guess I've since decided that's not that big a deal. What property of conductors allows them to conduct electricity while insulators can't? So some of the things that I emphasized on here, I don't really, you wouldn't expect to find on the test. I mean, this is just stuff right out of the notes, really. And the answer to that is conductors have free electrons that can move around from one atom to another. Whereas insulators, the electrons are locked into their particular atoms and can't move from atom to another atom. The exception is if you heat something up to enough till it becomes a plasma, then even insulators become conductors, like air becomes a conductor when you heat it up and you get that plasma arc between things. All right, so this is maybe a good question, practice question. The diagram below shows a sequence of events leading to the charging of a conducting plate. Complete parts 2 through 4 by drawing plus and minus signs to show the charges on the conductor and the insulator. And Jackson, I'm guessing you were kind of wanting something like this to work on your own rather than just. So I can make this available to you, but like I said, since I don't have the answer key, I don't know if it would be that helpful for on your own. So maybe I'll just go through
Yeah, I'm
some.
fine just going over it like
Okay,
some of the bigger points in class now.
sure. So use plus and minus signs to show the charges on the conductor and the insulator. So here we've got a neutral conductor and a negative insulator. So how that insulator became negative, it was rubbed with something that didn't really care much for electrons. So this has stolen a bunch of electrons from something. So then in picture 2, it looks like the neutral conductor has been placed down on top of the negative insulator. So think about how this would look different. In picture 2, I need to draw any positive and negative charges and where they would be. This is kind of, you could get your answer to number 2 fairly nuanced. Maybe I'm going to get a sheet of paper so I might draw with my camera here. Does anybody want to tell me what this would look like, what number 2 would look like? Like what charges would I draw and where would they be? Any takers? Maybe I should pick somebody. Put you on the spot. Let's see. Nora. So Nora, I've chosen you. The what?
Okay.
So if I were to draw, let me do the less nuanced one first. If I were to draw the charges on the neutral conductor, um, we've got positives and negatives in the first picture. In the second picture, what do I draw? Do I draw positives, negatives? Do I draw both? Where do they go?
Um, the positives would go more towards the top because they want to get away, right? I don't.
Here, let me reconstruct this. So I've got in step one, this is all negative, and then up here I've got far enough away that nothing's really it's not being influenced yet. There's the neutral conductor, and then in part two, I have taken this and put it right there adjacent. So you were thinking that the positives would move up to the top?
Yeah.
So there are a couple issues with that. One is, and I know I put you on the spot, so I apologize for that. But so you've got negative charges here, positive charges up there. What kind of charges repel one another? Like charges or opposite charges?
Like charges.
Like charges repel, and opposites attract. So
Yeah.
if anything, if these positive charges could move, they would move.
Oh, sorry, that's what I meant.
Yeah, I know. I'm always saying things backwards, so I understand. So but I don't know how picky I was on this test. Can the positive charges technically move? I know a lot of diagrams show them moving, but can they?
Yes.
It's just the electrons really that can move. So if I zoomed in on an atom here, this would be I've forgotten my chemistry. So I've got 4 protons here. Is that carbon, a boron, or does anybody remember the boron? Anyway, so we've got electrons flying around out here, and if this is one atom, would be a neutral atom overall, and then we've got this neighboring atom over here. This is if it is boron, then this is another boron, and it's got some electrons flying around here. I don't think boron's a metal, so this probably doesn't apply. But if this were a metal, this electron can be here, and it can also just travel over there. If we have some really negative source of electrons, these can move around like this. But the protons are stuck there in the nucleus. I don't think all of them can leave, but if the protons can move and the electrons can move, that the whole matter, the conductor would kind of fall apart. So anyway, protons pretty much stay in the same place, and I'm tempted to show that. I might draw it 2 different ways. So the protons don't move, but the electrons, they get pushed far away up to the top. I don't know if I did the right number. Now, in the textbook, the online textbook, they show positive charge moving to the near side and negative charge moving to the other side. And what they mean by that is, since the electrons are repelled by this negative, and that's going to leave this side positive. So it's as if positive charge moves closer to the plate and negative charge moves away. But don't forget that the positives really can't move. It's the electrons that do all the moving. And how about down here in the insulator? Do these negative charges move?
Yes.
Which way would they move? Away
Up.
from they would. So the way I've got this drawn, yeah, they would move up, but they can't. In an insulator, they can't really flow through it. I mean, what I'm showing down here, this only happens in metals, where you have the electron from one atom just flowing past another atom. So on a really microscopic basis, if I were to zoom in on this, and I had some atoms here, within those atoms, the electrons might be spinning a little closer, a little more time toward toward the top, and the nucleus is still positive. Rather than the electrons being evenly distributed, they're gonna try to get closer, but they can't leave this atom anymore because this is an insulator. And if both of these were conductors, if this were a conductor and this were a conductor, then what would these electrons do? Anybody? Nora's off the hook now. Can somebody else answer that? If you don't, I'm going to pick somebody. So if I just had a neutral conductor and a charged conductor and I brought them together, what would happen then?
The electrons would move into the neutral conductor.
Yeah. So this, the concentration of electrons in this overall neutral conductor up here is lower than the concentration here. Here we've got an excess of electrons, so these would flow into there, but since this is an insulator, they can't flow. All right, so all we've really gotten to is picture 2. You bring the conductor close to the insulator. The insulator, nothing really happens because the charges can't move. It just stays negatively charged, but it pushes away the negative charge of the conductor and sort of attracts the positive charge. Let me go back and see what picture 3 looked like. Actually, I think it's here. So now we've got the third step where a human is standing on the ground and comes in and touches the conductor. So if I put a person in here who reaches over, with his tongue, no, with an arm and touches there, what happens then? I'm gonna choose somebody. Edwin, you've been chosen. So what's going to happen here?
Really? I volunteer so much in class.
I know you do. I know, but you were randomly chosen.
Boy.
Do you wait? Do you want to opt out? Do you want to choose somebody else? Because you've earned that. You have volunteered so much in class. I think you do. Should I pick somebody else?
Wait, can I get a quick recap on what's happening?
Sure. So, in the beginning, we've got a negative insulator and then a neutral conductor, and the conductor has been placed on the insulator, and the negative insulator has pushed all the negative charge in the conductor to the top, away from the insulator, making the part near the insulator positive and the top negative. Now a person comes in and touches right there. What's going to happen?
Is the person gonna get shocked?
Yes. And
because the electrons are transferring kind of into the human because they've got some like positive charges.
Yeah, or just at least the way I've shown this person touching, this is there's a concentration of negative charge here, and these electrons, they're not only being repelled by these electrons, but they're being repelled by one another, and they want to get as far away from these and one another as possible. So once this person touches and the person's neutral and connected to the ground, that provides a path for them to go to a place where there aren't as many electrons, at least where the concentration of electrons is not as high. So we've got this ground, and no matter how many electrons you transport into the ground, it's still not going to make the ground negative, because the ground is this vast reservoir of neutral charge. So some of these electrons leave. So the next picture would kind of look like this. They're going out, and maybe I should erase a couple of them from my picture. So there we go. That next picture should look like that, and then finally, who's this? Clarity. Picture 4. The person lets go and walks away, and then what do we have in the end after the person lets go and walks away? So we're going from that down to this final picture. What should I draw?
Would it be similar to how it was in the second one, except there are less electrons in the top?
Sure, yeah, would be right. So I've already gotten rid of a couple of electrons right there. So when the person lets go, what changes? Like, does it stay just like that? I've got this one electron over on the left, and I've got these 3 positives down here.
Well, the one electron would like stay at the top, probably like more towards the middle.
Exactly, yeah. So these 3 positives are attracting this electron still, and it's going to be pulled toward this one, and it's going to be pulled toward that one, and pulled toward that one, and the net effect is it's going to get pulled to the right, and that'll keep happening until it gets to there. So in this last picture, it's going to look something like this. The insulator hasn't changed the whole time because its electrons can't really leave. The bottom of the plate's still positive, but the top of the plate is less negative than before. And if we remove this thing entirely, if I just got rid of the insulator basically, then everything would spread out and even out. So I don't know, maybe the negative would be in the middle, and then it's hard to imagine this. The way the textbook does it, I'm just going to draw it kind of like this. So we have this even charge distribution, but overall we would have a positively charged conductor on top. So let me go back. I keep clicking the wrong places. Going back to this, sequence 3 show the movement of charge, so the movement's going into the person. So we're good there. All right, so that's pretty much that one. Number 4 and 5, these come from homework questions. Why do most objects contain nearly equal numbers of positive charges? So right now, I'm just about even. I've got like 20 trillion positives and 20 trillion negatives, and I generally stay that way. Does anybody know why? If I had 20 trillion and 10 negatives and 20 trillion positives, and I sat down in this chair, or I flew down and landed on the Earth's surface, what would happen to me then? Anytime I get charged up and I touch the ground, my excess charges are just going to flow right into the ground. So that's the answer to number 4. Things are just about always neutrally charged. That's why we don't usually deal with static electricity much. Except one of the most annoying things, I meant to bring this. Has anybody ever broken up styrofoam to try to throw it away, and the little pieces of styrofoam stick to you, and you can't make them stop, and you try to rub them off? Does anybody know why it's so hard? Most things are not charged, but styrofoam is, and you can't really get it uncharged. Why is that? What is it about styrofoam?
Is it an insulator?
It's an insulator, exactly. So
But it's already charged,
Right.
so it can't get out.
yeah, so in order to remove the charge from an insulator, it's a lot harder, because if those were little tiny steel balls that were stuck to you, they would, all you have to do is stand on the ground, and any excess charge in those balls would go into you and into the ground, and they just fall off. But the insulator, it's really hard. There's apparently some kind of spray that you can use to deionize things, and dryer sheets that you put into your dryer to try to minimize static cling. They somehow use ions to get rid of the charge of insulator type materials like sweaters and sweatshirts and stuff that you pull apart in the laundry and it's still stuck together. If all those things were metal, that wouldn't happen, but it wouldn't be comfortable. So what does it mean for something to be polarized? That just means charge gets separated. You have positive charge on one side, negative charge on the other. And that's what happens if I take a balloon and I put it up next to the wall. It polarizes the wall. If this is a balloon I've rubbed on my head, so let's say this is a positive balloon, I bring it over to the wall, and the near side of the wall then becomes negative because it attracts those negative charges. But if I take a negative balloon, hold it by the wall, the near side of the wall becomes positive and the farther part of the wall becomes negative. Let's see. Here's one. A neutral atom has 8 protons. What's its net charge in coulombs? When 2 electrons are added to the atom. So, does anybody know how you would solve that? Neutral atom has 8 protons. What's its net charge in coulombs when 2 electrons are added? Anybody just tell me the answer? You ought to be able to do this one in your head. So, you can't do it in your head. Oh no. This would be, so I'm not going to draw the whole atom. I'm just going to, here's the nucleus. We have 8 protons, and then around here we've got 8 electrons. And I know that because it's neutral. But then somehow I add a couple of electrons to it. And it probably wouldn't like that, but let's just say I could do that somehow. So it's got 2 more negatives. Now it's got 10 electrons and 8 protons. So its charge is 2 electrons. And what's the charge of 1 electron? Somebody's got this in your head, I'm sure, after doing all these problems.
1.6 times 10 to the something.
10 to the negative 19. Yeah. So it's just going to be 2 times that, but it's negative because they're negative. So the answer is negative 3.2 times 10 to the negative 19 coulombs. I keep going to that. So unusual to have a Word document that I'm working from. Let me skip down a little bit. Let's see what. Hey, this might be a good one. A tiny object has 5 times 10 to the 8th more electrons than protons. What's the magnitude and direction of an electric field 2 meters to the right of this object? So see if you can think of how to do that one, and I'll work that one out on my paper while you're thinking about that. I'll zoom in a little bit better so if it's small, hopefully you can read it. Alright, I have to make a terrible confession. I've forgotten the order of magnitude of the Coulomb law constant. 8.99 times 10 to the, is it 9th? Does anybody remember? Can somebody?
Yeah, 9th.
Okay, alright. Clearly I don't use that a lot. So you need that in this problem. So I'll just go to, I haven't completed my solution, but here's what I've got, if you were wondering how to do this. So this is one of the electric field equations. The basic electric field equation is force per unit of charge, so force over charge, and the electrostatic force equation is K times the first charge times the second charge over R squared. And that would be a force that, let's just say I have a positive here and I've got another positive there. this equation gives me the force between the two of these. So if I take this force and I substitute it in here, you can see I would have K Q1 Q2 over R squared, but it's also over Q. So one of these Q's cancels out. And the Q that cancels out is the so-called test force or test charge. So just imagine this is the charge creating the field. This is the so-called test charge out here that's experiencing the field and experiencing the force. So if I write this as big Q, which is this, times little q, which is this, this would give me the force between them. And if I divide this whole thing by little q, then the q's cancel out, and I get kq over r squared, which is where that formula comes from. This will be provided on the test, but just showing you, you don't really necessarily need it. You just need this one, and those are all you need for the test. So the electric field is K, which is here, times the charge. To get the charge, I know that there are 5 times 10 to the 8th electrons more. So everything before those 5 times 10 to the 8th electrons, that's all going to cancel out. So the charge comes from this many excess electrons, and each electron has this charge. So that would be what I would plug in for Q over here. I'm not even going to do it, but it would go here. I'm not going to bother to multiply it out. And then the distance between these, the distance from this charge, so the way it would look in my picture, this is Q. This is creating the electric field. And I'm not going to put a plus or a minus because I don't know that I know enough yet to figure that out. So anyway, that charge would go here, and I would figure out the charge this way. This is the distance, 2 meters, to this little point right here. So we're just imagining what is the value of the electric field right there at that point. So 2 meters is the distance to that point from the charge. So that's how it would calculate the electric field. But the direction is is what I think is the interesting part. Actually, you know what? I do know the charge. Is this thing that's creating the electric field, is it positive or is it negative? Let me go back to the problem because I'm kind of getting lost, and if I'm getting lost, you're certainly getting lost. A tiny object has this many more electrons than it has protons. So the tiny object's creating the electric field. What is the charge of the tiny object? Positive or negative?
Negative.
Thank you, Jackson. Yes. So this is a negative charge. And if I were to draw the field lines around this negative charge, remember that they go towards a negative charge like this, and that means if something is over to the right of it, the charge is, or the electric field is going to be that way. So I can calculate the electric field using this formula, and then in terms of direction, the direction of the electric field is going to be toward the charged object. If this were a positive object, the direction of the electric field would be away from the charged object. And since it says it's 2 meters to the right, toward the charged object would be to the left. And here's an acceleration one. So at this point, do you have more, does anybody have a new question that's popped into your head? Okay, would you like me to work through number 10, or would you like to try number 10 and see if you can? Okay, so wish there were a way I could zoom in without it going off my paper. I just kind of want it to come down to the next line. Let me return, and then return again. So I can make it bigger. I guess I could have changed the side. So there's the problem. An object has a mass, and I'll actually get out my calculator this time and find the answer. mass of 3 times 10 to the negative 10th kilograms and a charge of positive 20 nanocoulombs. So nano, does anybody remember what nano means? These would be good metric prefixes. If you're going into the STEM field, it's good to know what nano and micro and pico even means. So nano is 10 to the negative ninth. So it's 10 to the negative ninth coulombs. If the object is accelerated leftward at a rate of 500 meters per second squared, what is the strength of the electric field that the object is experiencing? So it should say accelerated leftward by the electrostatic force. So we can assume that it's the electrostatic force that is causing this. And you have to find the strength of the electric field. I'm going to get a new sheet of paper to do my work on. I don't know why I didn't ask for the strength and direction. I should have asked for strength and direction of this electric field. So I'm going to switch now to my little picture on the paper. So here's the particle, and it's 3 times 10 to the negative 10th kilograms in mass, and it's accelerating this way at 500 meters per second squared. And its charge is 20 times 10 to the negative ninth coulombs. And I'm looking for the electric field. So I've got a couple of different formulas for electric field. I'll pause in just a second in case you want to do some more work without me interrupting you. One is just the basic one, force over charge. And then the other formula for electric field is the one I just used a minute ago, which is the combination of, I would substitute in the Coulomb's law formula for force into here, and that would give me K Q over R squared, where Q is the charge that's causing the electric field. But just looking at these two formulas, guess which one is most appropriate for this problem? The one on the left or the one on the right? Raise your hand.
The one on the left.
The one on the left, yes. So this is actually not a really hard problem. There's that, and then you're going to need one other formula for this problem. What's the other formula?
Acceleration equals force of the electric field divided by the mass.
Yeah. So it's just another version of Newton's second law, F equals ma. So with these two formulas, you should be able to figure it out. I'll give people a little time. Wish there were a way to freeze my screen, but I don't know how to do that. Oh, I know what I can do. I can just do this, and then I can work down here. I'm going to do Mr. Pennington method here. right. Does anybody have an answer to share? Actually, if you do, just put it in the chat. And it's too bad we don't have. I'm realizing one of the advantages of Zoom is the private messaging, so you could privately share your answer with me, but try not to look at the chat until you have your own answer. Jackson, I'm an order of magnitude different. Maybe I don't know if let me check my calculations again. Okay. So Clarity got the same thing. Maybe I'm the screwy one here. All right, so even if you're still working, I'm going to go ahead and reveal what I got. I got 750 newtons per coulomb. So maybe I'm screwing up. I'm feeling like it. Yeah, everybody's getting different answers than me. So here's what I did. Tell me where I messed up. The electric field equals force over charge, and force in this case is, we can find it with MA. So I could just say my electric field equals MA over Q. And the mass is 3 times 10 to the 10 negative 10 to the negative 10th kilograms. And the acceleration is 500 meters per second squared. And the charge is 20 times 10 to the negative 9th coulombs. So
That's exactly the work I had, and I just put it into my calculator again, and I got 7.5.
7.5. Here, well, watch what I'm doing. So I'm getting, oh, yes, you're correct. 7.5. I was just going the wrong way. So here's what I did. I'm just doing bad mental math with exponents. So I just did the 3 times 500 divided by 20. And I get 75. And I was thinking, oh, it's to the 10th over 10 to the 9th, so that's going to give me to the 10th. But it's 10 to the negative 10th divided by 10 to the negative 9th, and this is an order of magnitude bigger than that. So I need to divide this by 10 instead of multiply by 10. So there's my mistake. Good job. You all did better than I did. So it should be 0.75 times 0.75 newtons per coulomb. But now the question is, what's the direction? So think about that. If you haven't written down a direction yet, figure out the direction for this. Okay, so if you think it's to the left, raise your hand. Anybody else? All right, Jackson and Edwin, you are correct. It's to the left. So I'm just going to write leftward. The direction of the electric field is always in the direction of the force applied to a positive charge. And since this is a positive charge, and since it's accelerating to the left, there's a force to the left on this positive charge. That means the electric field is to the left. If this were a negative charge accelerating to the left, then we would have known that the electric field was actually to the right, because negative charges move opposite the electric field. So we're about out of time. I think I'm not going, and that's the end of this old quiz anyway. So if anybody wants to ask more questions, you can, but I think it's also a good time to jump ship if you want to head out. So
Thank you.
you're welcome.
Thank you.
You're welcome. Leslie, Ollie, do you have any questions or issues to discuss?
I do have one.
What's that?
It's because I haven't taken a test online with you yet.
Yeah, yeah.
I don't know what the process is.
So I'll show you in Google Classroom what it'll look like. I'll show you our last test.